In the previous movie, we set up the IK-FK matching for the foot and manual pole vector knee control. In this movie, we'll finish our matching script by snapping the automatic no-flip knee to the result knee position. Open the file Character Rigging, Appendix A, Part 5 Start, and load the Match App script into the script editor, or use your own files from the previous lesson. Before we start iterating on our script, let's first add some UI controls to our Match App to allow the animator to choose which of the two different knee modes to snap to. We'll copy the same format we used for choosing between the IK and FK forearms to maintain consistency in our app design. But of course, we'll change all the labels and names to fit our legs purposes. As with the IK arm matching procedure, we'll have to add a parameter to pass in the requested knee mode. No matter what mode we're in, we can match the foot control the same way, so we won't touch that part of the script. However, we'll make some adjustments in this section of the script where we calculate the knee's new position. If the knee mode is equal to 2, meaning the second radio button is currently active, then the knee is in manual mode. In this case, we can rely on our existing code to snap the knee control to the left shin result joint. We also need to turn on the manual knee snap control. If the knee mode is not equal to 2, then our knee is in automatic mode, and we have a little more work to do. Before we worry about matching the knee position of the automatic no-flip knee to the result knee, we first need to set the length of each joint. Remember, this is controlled via two distinct attributes on the foot control. To do this, we'll actually need to consider two factors. First, the individual stretch value of the thigh and shin joints. And second, the overall stretch value of the leg, due to the foot control being moved away from the body. First, let's calculate this overall length factor. Recall that in Part 13 of the Character Rigging tutorial series, we achieved an overall length stretch via a driven key applied to the thigh and shin joints. When we created this driven key, Maya automatically created a corresponding animation curve node in our scene. We can find this node by first selecting the length node that drives this driven key. Open the node editor and show the node's connections. As you can see, its shape node is attached to several animation curves. Since both the pole vector and no-flip legs are attached to the same foot control, they both stretch at the same rate. Thus, to figure out this stretch factor, we just need to compare any of these output values to that leg portion's typical length. Return to the script editor, and in the left leg IK to result procedure, create a new variable named leg length factor. We'll use the getAttr command to retrieve the output value of the shin's no-flip IK joint translate X animation node. Then we'll divide that value by the default thigh length, which you'll remember is already conveniently stored in a variable for us. Next, we'll use that value to help us determine the thigh and shin's individual lengths. Start with the thigh by creating a variable named thigh length factor. We need to take the current length of this limb and divide out the leg length factor. Doing this will take us back to a normal sized leg. Then, we just need to divide that value by the default thigh length. Taking basic math into account, We can condense this by dividing the joint's current length by the product of the leg's stretch factor and its default length. Repeat for the shin. Now set the resulting values to their appropriate attributes on the foot control. And don't forget to add a line to switch to automatic knee mode. If we test the script now, you can see that each portion of the leg scales correctly. Next, we need the knee to line up properly. Like the thigh and shin lengths, the orientation of the no-flip knee is controlled by a knee twist attribute on the foot control, as opposed to a physical control in the workspace. The most straightforward way to line it up would be to gradually increment the knee twist, while continuously testing it against the result knee's world space position. However, because our knee position can be any decimal number, we'd have to increment by the smallest value possible at each interval, 0.001. This would make the process extremely slow. Testing the values from 0 to 1 alone would require the script to iterate 1,000 times. Instead, let's be a little cleverer about this and increment the knee twist by a larger amount. If we compare it to the result knee and find the angle too great, it means we've rotated too far, so we'll then decrement, but only by half our initial amount. Otherwise, if the angle is too small, it means we haven't rotated far enough, so we'll increment by half the initial amount. With each repetition of this process, we come closer and closer to our actual value. This is a technique known as bifurcation. In order to find the current knee angle, we'll need two vectors. One from some arbitrary point in space to the result shin joint, and another from that same point to the shin's 0 position, representing the knee's default angle. First, set the foot control's knee twist to 0. We can store the two world space positions of the no flip and result shin joints using the xform command. Notice we're explicitly declaring these as arrays by using these square brackets. Like we showed you in part 1, this is so we can store the three spatial position coordinates. For their shared center, let's use the no-flip foot joint. This will give us a common origin around which to measure our angles. Once we have an origin and 2 points in space, we need to find actual vectors that move from that origin to each point. We can do this by assigning a pair of variables the difference between the result shin position and center point, and the no-flip shin and center point, respectively. Now that we have these vectors, we can use Mel's angle between command to find the angle between them. We'll use the v1 and v2 flags to assign our center to result and center to no-flip vectors, and store the angle in a variable named delta angle. The angle between command stores 4 values. The first 3 represent the axis on which the angle is measured, while the last value represents the angle itself. We don't need to be too concerned with the axis, because the other angles we compare it to will be on the same axis. We're just interested in the actual angle itself. Now that we have this value, we have a base point to start comparing our test runs to. In order to actually perform these test runs, we'll need to create a new procedure. Name this one Iterate to Match. Like the parameters we passed into the IK-FK matching procedures before, this procedure will need some information to perform its task. First, it needs a node to test, in our case, left shin no flip IK joint. We'll store it in source node. Next, it needs the position of the center point of the angle. After that, it needs to know the driving attribute that affects change on the source node, and the vector of the shin joint's default position to use as a base for comparison. And of course, we need to feed it the target angle we're looking to match. Finally, since this is an iterative task, it needs to know the next value we want to try, as well as how many values we've tried up to this point. We'll also modify this procedure to return a floating point decimal value. This will allow us to send back the appropriate knee twist value once we've found it. Now that the procedure is set up, the first thing we need to do is set our drive adder, the foot control's knee twist, to our first test value. This will rotate the no-flip leg. We then need to calculate the vector from the no-flip shin's current position to the center point so we can find its angle. Remember, to do this we must first store its world translation value. Then subtract the zero pos vector from it. We can then use the angle between command once again to find the angle between them. Now we have an angle to compare with and an angle to compare to. However, like matching the arm lengths in part 3, remember that in a computer system we're dealing with precision values. Because of this, it's unlikely we'll ever get two values to match precisely. So like we did then, we'll instead subtract the current angle from the target angle and consider a value with a tolerance of 0.01 to be acceptable. If we're within this tolerance, then we'll return the value we've discovered using the special return keyword. We're also going to add an escape condition here. If it takes over 10,000 tries to match, then we'll cut out of the iteration cycle early. We do this mainly to avoid system crashes due to too many computations. Now, if we haven't found the value we're looking for yet, we need to compare our current angle with the target angle we're looking for. If the current angle is greater than the target angle, then we need to decrement our current knee twist value by half the value we previously tried. Likewise, if we're still coming in under our target angle, then we'll need to increase it again by half our previous value. Now that we have a new value, we'll run our iterate to match procedure again, within itself, to test our next best guess at the correct knee twist value. This is a technique known as recursion. This time, we'll increment our count value so as to continually keep track of how many times we've gone through a recursive loop. And we need to make sure to return the value. This will allow the final value, the one that eventually escapes the loop by fulfilling our tolerance or count condition, to bubble up to the top. Now we can call our new procedure from within the left leg's IK match procedure. We'll attempt to match the shin's no-flip IK joint using a vector from our center shin position, the foot joint, and which rotates using the knee twist attribute to match our delta angle. We'll start our first iterative attempt at 90 degrees on our 0th try. Try testing the script again. This time, the automatic knee matches the result leg. While trying different knee positions, you'll notice the script sometimes reacts very quickly, and other times reacts a little more slowly. This is a product of where the exact angle falls within our recursive process. Sometimes it only takes a few loops to solve. Other times, when values fall on the fringe of bisectional values, it can take many more. However, with enough iterations, we can almost always find the right value. One thing you will notice though, is that if we position the knee on the opposite side of the leg's z-axis, the script fails. Why is this? Because Maya's angle between command doesn't return negative values, consider that there are actually two possible correct vectors for every target angle. Because we started our search in the positive direction, our script will always find the match on the positive side. This is easy to fix, however. First, we'll store the knee twist value in a new variable. Next, we'll query the world space position of our no-flip shin joint after we've found that twist value. If we compare it to the result shin, once again using a tolerance value, and find that it's not in the same position, then we know we've actually found the inversed value. Then we can just invert the value of the knee twist. As always, copy and adapt the new portions of script for the right leg IK to result procedure. Keep in mind that you can reuse the iterate to match procedure you created for both the left and right legs, since we made it generic. With that, our snapping script is complete. Once you have access to a tool like this, you'll find the process of animating between IK and FK modes much faster and more straightforward.